Good morning. Sorry for the delay. How's the sound? How is the sound? Hello, Gerardo. Sorry I'm late. I'll go right to 12 o'clock today to make up for the time. I usually do that anyways, it seems, but I'll just wait for people to come in. Okay, sound is good. Good morning. So hopefully you did find time to do the review of the SDS videos, sampling distribution of a statistic, and to look at the notes and the answers provided to the questions posed. And I really want to pick up with inference. And today I am going to be ambitious. We're going to finish inference on a proportion and get into inference on the sample mean. And then if we have time, I'll discuss the t-table. And then next week, I will continue discussions and then have the test after class. And I said I would give you the test, what did I say? From 1 p.m., right? We said 1 p.m. Do I say till 6 p.m.? It's all on video. I should watch it. I should write things down, right? I have so many things written down you wouldn't believe. The little slips of paper everywhere that I need to organize. So writing it down is not going to be the solution at this point. So I think the test will be from 1 p.m. to 6 p.m. and then the final exam will be on I believe it's May 15. And I will post it at 9 a.m. And you can have till, what did I say? Did I say anything about this? 3 p.m. Does anybody recall? So I will write those down in the proper place. Not on pieces of paper. Okay, so the final exam is a little bit of everything. Oh, and the test 2 will be May 1st. Again, the test should only take you an hour and a half, and the final should not take you more than 3 hours, but I'm going to double the time. I'm going to double the time. Okay. So, shall we start? So make a note and hold me to it. It's here in the video if we have any problem with recall. I want to make my screen a little bit bigger. Okay, so we left off discussing, unless you have any questions, we left off discussing confidence interval. So what you need to do from here on out is to print out the formula sheet and the tables and have them at hand. Have them nearby. So we've already discussed covered this first one, and I said if you see a problem like this, you're looking at the bin section or SDS on the binomial x, or the count variable. I'll just write that. And SDS stands for sampling distribution of a statistic. The second one is for, as a result that you have for SDS, sampling distribution of the statistic sample proportion. And then finally, last thing that we talked about last class was the sampling distribution of the statistic x bar. So these are variables. And they have a distribution, and we talked about deriving the distribution and using it to make predictions, answer questions. And that brings us to 4. That brings us here where we are now today. So this is going to be a discussion about inference. So in other words, I'm telling you where it applies. So in inference, P is unknown. That's different than up here. In these cases, we know the parameters, right? Like in number 1, we know P, or we wouldn't be able to do this. And number 2, we need to know P, or we can't even do this. And in number 3, we know mu to be able to do this, or we can't. But when we get to inference, it's a new setting where we don't know these parameters. I need to make this stick. All right, fine. Okay. So what we did last class is I discussed the confidence interval. I introduced the concept as though what you're doing is creating an interval around your point estimate, the best guess of the parameter. So if you don't know P, the best guess is take a sample, a good sample, and calculate the proportion of success is what it is you're looking for. and then create an interval just like we do, 1 or 2 standard deviations around the mean, etc. But we say specifically we're going to take Z star standard deviations around the mean, around the estimate. We treat this as though it's an estimate of the mean, or the expected value, let's say that instead. So p hat is an estimate of the expected value p, which we are trying to find, and we're going to build an interval around it to present that in a report or in a study, publication, or manuscript for publication. And because we don't know p, we also, using the theory, we estimate that the standard deviation should be that. All of that is taken from number 2, the results of number 2. So what we have for confidence intervals are replicated I gotta move this up. We replicate that for this case when we do it for inference on the sample, inference on mu unknown. You don't know the population mean, but you want to make an interval using sample results. So this is very realistic. This is what we do, right? We use the theory in the realistic case that we don't know these parameters and we try and estimate them. So these are the intervals. P for proportions, right? So examples are people who favor a policy, proportion of people who get divorced, and things like that. And means are for problems where you're measuring the mean. Average this. If you have a problem, you're trying to find the expected value of height of children in their preteens. If you're trying to estimate the average sales, right, you're going to use this approach. But the pattern is the same. What is the pattern for a confidence interval? The confidence interval, let me move this away. I want to nope, that's not what I wanted to do. All right, let's just leave it. Okay, for the confidence interval, I'll put it here. Confidence interval. In general, this is the general approach. You take the point estimate, the best guess, the unbiased estimator, and you add and subtract what's called the critical value. That's how many standard deviations you want to go away from the mean, around the mean, to capture a certain percentage of the observations. So critical value. And then you multiply that by what's called the standard error. Which really is the standard deviation. So it's like, so it's like when we do mu plus or minus 2 standard deviations, we're trying to replicate this concept of how we use the mean and standard deviation, okay? But instead of saying mu, we say point estimate, so it's general. Instead of saying 1, 2, or 3 standard deviations, we now introduce the more generalized critical value, and instead of using standard deviation, we call this the standard error because it's an estimate. It's not really a population parameter. Oh, somebody wrote something. Okay, Gerardo, I'll look at that in a second. I'll do that one. Okay. All right, so the question that you're asking, Gerardo, has to do with number 2 here. But let me work with this right now, and then I'll go back. Okay, so in general, you see point estimate plus or minus critical value standard error here as well. Point estimate plus or minus critical value standard error, and then here as well in number 6, but we'll talk about that later. Okay, so let's get back to the problem. Okay, so what we were going to do here is compute, compute the, we've got p hat already. And then we just have to use it. We got the critical value, we figured that out, didn't we? It's over here. So we looked at how many observations, 98% of the observations are within, so we had to find this critical value, which we found using the new table, table T, although we could get it with the Z table. It's just more precise in the T table. And then, so we have that, we have that, and then we just have to calculate this. So let's make that calculation, 0.547, and then, where am I going to write it? Going to take this with me. So this is what we have. So we got to calculate 0.547 times 1 minus would be point, so that's 3, and that's 5. 4. And then divided by n, which was 53, and then you take the square root. So this is called the standard deviation of p hat. You might see these symbols, and it's the estimate, so I would write it like that, I guess, because it's an estimate of an estimate. I guess this is 5742, but I took 3 decimal places. I took just 3 decimal places. don't forget to take the square root. So 0.547 times 0.453 divided by 53, and then square root. And you get option B. Okay. Okay, any questions about that? So when do you do that? You do that when you're asked to create a confidence interval, and you do it for the proportion when you have information about a proportion. I mean, I don't know how else to say it. See, it says even true proportion right here. That's how you know how to do that, why to do that. Okay, so next. The next thing to do is, back to my formula sheet, I'm going to combine these two terms and give it a name. We call this the margin because it's what you add and subtract on either side. It's a margin, and it's the margin of error. So because of the variability, we allow some, we provide a variable of alternatives around the point estimate because we might be off, right? We're not going to necessarily get the exact proportion. So we create an interval. So we call that margin the margin of error. So what we want to do is, before, in advance of even taking a sample to calculate or to infer about the population proportion, we want to know what sample size we should use. We want to figure out what sample size we should use. So what we're going to do is, in this case, you see the sample size would be here. Before we take a sample, what should the sample size be in order to do what? In order to get an amount of precision that we're after. So what we're going to do is, we're going to take the margin of error and we're going to sort out what should be the sample size to get a particular margin of error with a level of confidence. That's what we're going to do. So we're basically going to use algebra to isolate n, where we call this m, this whole thing, the margin of error. So this is what we're going to do. All right, so what I want to do is trying to, all right. So here's an example of a problem. Compute the sample size you would need to obtain an estimate of p within a certain margin of error, m. Or we could say within a certain width, and that would be 2m. With C% level of confidence. So this is a general formula. So I'm going to set this entire thing to m, the margin of error, and isolate for n. So this is algebra. I'm I'm going to do this with m over z star. And then what I have to do is square this to expose what's inside. And then what I need to do is invert or flip those variables, putting n here, and then flip this so it looks like that. So this is the formula for the sample size. Any questions so far? So all I did was say that I knew m, say I know z star, and we'll figure out p hat in a moment, given p hat, and then you can isolate for n. And so I found a formula that will help me figure out what sample size I need with these conditions. So just a point about p hat. So what are we going to do here? So let's say, so what's p hat? P hat is the result of a sample, so it's kind of strange. Why do I need a sample size in advance when I already have one? Well, let me see in the notes because I wrote it here. There are 3 cases for p hat. Case 1. Suppose we are told p hat, just like we've been told information from on high through all these other problems until now. You know, I give you p, I give you mu, I give you, it's just a candy store of parameters. But if I was told p, then I can use that as my p hatter. I'm going to give this special name p star now to put that in the formula. Don't confuse it with this z star, that's the critical value. But when I solve it, yeah, I put it like this, okay? And then just a point, when you solve this for the sample size, always round to the nearest whole number. So for instance, if you have as a result, if n equals 37.1, you round it to 38. And you do that because, remember, the larger the sample size, the more precision you have, right? If we go to the formula, if you think about it, margin of error is equal to z star p hat 1 minus p hat over n. So margin of error is smaller the larger the n. So if you increase that denominator, the m goes down, and you want more precision. You want a small margin of error. So that's why to maintain a margin of error, you have to go all the way up to make sure that it's small, smaller than you even forced it to be. So case 2, back to p. So let's say if p is not given, but there is some other simple random sample that we had, someone did previously and got some information, and you don't have any information that p is, the true proportion is equal to 50%, then what you should just do is use the results of the previous sample. Okay, so just use p star equals p hat. So far we have, if you don't know, if you know p, just put it in there. If you don't know p and you have no reason to believe it's just 50%, then if you have a previous sample that someone's taken, use that one, that result. If you have absolutely no information, let it be 50%. Because that's in the middle, right? That's in the middle of 0 to 1. Because proportion could be between 0 and 1. Why not just go halfway? That doesn't bias. That's like an unbiased approach, I guess. So P, because P is in 0 to 1 somewhere. So let's go through this. So P is the actual true proportion. P hat is the estimate of the true proportion from a sample. And I'm using P star for the formula because I'm saying it can be so many different things. It could be the P that someone told me. It could be the P from another sample, or it could be nothing that I know. So I'll just put 50% in there. So we substitute in the formula then P star. So that brings us to our problem. Let's do this problem together. Remembering those criteria in that case, those different cases. Suppose we wish to estimate the proportion of Canadians who actually understand the Constitution of Canada. What is the approximate number of Canadians who need to be sampled so that 95% confidence interval has a width of 2 percentage points? So solve for n. From above, we have in the box, n is equal to z star over m squared p star 1 minus p star. I call this the Mazda formula, zoom zoom, just to remember it. Because you're going to have the formula sheet, but if you didn't have it, you have to have some sort of way of remembering this. I mean, you could derive it every time, but it's z star over m squared. Success, failure. So z star for 95% confidence interval is 1.96. I got that from the table. Remember, we're using this t-table now. So I'll practice using that. And you see, for 95% confidence, z star is 1.96. That's all we've learned to use, how to use this table so far. So 1.96 m, what about m? What is m? M is equal to, well, confidence interval has width 2 percentage points. Width of 2 percentage points. Width, well, margin is just 1/2 of the width. Margin is just 1/2 of the width. So to be 2 percentage points, it would be like 1/2 of 2 percentage points. So m is 0.01. Any questions about that? So there's width is equal to 2 margins of error. Okay, so yeah, it's from this. So if width is equal to 2m, then m is equal to 1/2 width. Is that okay? Think about that a moment. So then do we have everything? So what should we use for P star? So I'm gonna leave you for a minute or two. I'm gonna go get a drink of water. Okay, I'm back. How'd you do? What did you get? So yeah, I got the Z star from the T table at the end. Now you could also get it from the Z table, because what does it mean? It means where do you have to be to have 95% in the middle if this is the standard, this is the normal distribution. Where should you be? How many standard deviations from the mean? So to figure this out, it's 95 in the middle and it's 2.5 on the either end, so this is 0.250. So you have to look inside and out for that amount to find out the limit. So you could go to the regular Z table to get it, but it's longer, so we have a faster way. Let's use it. So if I go to the regular table and I looked for 0.025, it should be around 1.96. So see? And that corresponds to 1.96 negative. You can take a screenshot. And that's also why it is 1.96. So it's negative 1.96 because of the way that it's drawn. And the way that I looked at this side, so it's negative, but that means 1.96 below and 1.96 above. But I did grab it from the T table. So how did you do? So let's plug it in and interpret. One thing is to do the math, and the next is the interpretation. So 1.96 m 0.01. Don't forget to square, and then we're going to use, there's no information, absolutely no other information about what p could be, so I'm going to use 0.5. I'm going to use p star equals 0.5 because there is no information. So these are my parameters, or my details here. This is what I put in the formula. And then I get the sample size. And then I have to interpret. So what do you get? No answers? Right, okay, you guys. So you got 9604, and then you have to interpret And then you have to say, well, we want to maintain a margin of error of 2 percentage points, sorry, 1%. So this would make it exact, but that's not among the options. So the question is, do I round down or do I round up? And rounding up is always better because the higher the sample size, the lower the error, right? So lower margin of error, and that's going to maintain my 2 percentage points. It'll be even smaller, but that's fine. At least it doesn't exceed it. So I'm going to round up to 10,000. So very good job for those who got it. If the options were, if there was an option that said 9,600 or 10,000, you still pick 10,000. It's not about being close. It's about maintaining margin of error no larger than 2 percentage points. Remember that point. All right. Shall we continue? So I see very few people on here. Maybe it's because people are not caught up and they just think it's a waste of time. I'm going to encourage everybody, if you're in contact with the other students in the class, that they should just attend and sit back and watch, and maybe they'll get something even though they're not caught up. Just not to delay exposure to the material. Good morning, Toussaint. It's my Haitian students are chiming in. All right, they're getting their stats review. Okay, so let's go on. So here we are. So what we've done so far then is talked about the first column, which is confidence interval estimation. The second column of the formula sheet is sample size estimation. And the third column of the formula sheet is about hypothesis testing. So let me go to the formula sheet here. And so we've done confidence intervals, sample size estimation, and we are here. So let's take a moment and stare at this together. And this I do not know how to operate with this thing. I gotta get rid of it. Nope. I'll just leave it down here. Okay, so let's look at this together. What is this? Actually, let's look at the whole row for a minute. Notice, as I mentioned, this is inference. So we don't know P. We don't know P. Notice there's no P in here. There's just P hat, the sample result. And there's no P in here. There's just P star, which is, we discussed our best information on P. And if we don't have any information, we use 50%. And then here as well, there's no P, we don't know P. So this is all about not knowing P and coming up with estimates of P. In this case, here we have a sample size to estimate. Oh, sorry, we compute the sample size we need to be able to estimate P. And here, what is going on here? What is this? Things should look familiar. This looks familiar. This looks familiar to us. What is this thing here? Right, so this is the standard deviation of P. This is the standard deviation of P if it's the standard deviation of P hat, to be precise, the sample proportion, if P was actually equal to P0. That's what that is, okay? So good. That's the standard deviation of P hat if P was actually, so what does this mean? This is the standard deviation of the sample proportion, a result of a sample, if the true proportion was equal to a number P0. Okay? And if the true proportion was equal to P0, this is the mean of P hat if it's the mean of P hat if the true proportion was equal to P0. So what you actually have here is a value minus its mean divided by its standard deviation. Notice the x, the variable, is P hat. The mean of P hat is P0 because that would be the true proportion, and the standard deviation that we're dividing by is this because that's the standard deviation of P hat if P is equal to P0. So what I'm using here is, this is standardization, that's why it's Z. This is a standardized score. I'm standardizing the statistic P hat, or the variable P hat. And where am I getting this from? Number 2. Up in number 2, you see this result again? So you're going to feel like you're on you're going in circles because everything comes back at you, okay? P hat has a mean of P, so what does it mean again? It means that a sample proportion on average will be the sample proportion from repeated sampling. That will generate a distribution, and in that distribution, the mean of all the P hats of all the possible samples should be the true one, and its standard deviation should be this. So if I have a P hat, and if I have a P hat from a sample and I standardize it, what I'm doing here is if I assume that I know the real P and I standardize it, then the sample P hat result should be no different than the hypothesized value. So what we're going to do with this is see if these are close enough. If our hypothesized value is with a reasonable distance from the sample value. Okay, so if you didn't understand what I just said, it's fine. I'm going to repeat it. But what you should see here is that this is a standardized score. So let's look at an exercise, and I'm going to demonstrate how to solve these problems in 5 steps. And you can use those steps, but in the end, for the test and for review exercises, I don't always ask for all 5 steps to solving these problems. So but you should practice with all 5 at any rate. It makes you, much more capable of answering questions on just portions. All right, so let's go to do some problems just to wrap up what I just said. This is all about not knowing P and trying to estimate it. One way to estimate is take a sample and then use the theory about sample proportion, that's in number 2, to create an interval that we call the confidence interval. We can do that and collect a sample, but first we might want to know the sample size to collect, so this helps us do that. Not even knowing P, we just use 50% to substitute in there. And this comes from setting this to M, the margin of error, the give or take. And then finally here, what we're going to do is we don't know P, but we're going to guess what P is, and then we're going to test against a sample to see if the sample result is within a decent range of the hypothesized value. If it's not, then we're going to throw out our assumption of the hypothesized value. That's what we're doing. All right. So you can take a screenshot. I'm going to move on. Okay, I'm going back to the questions. So let's try this. Okay, so I have a summary here of what I'm going to do, but let's just do it. Let's just do it. Okay, so here's my first exercise. So a random sample of 900 individuals has been selected from a large population. It was found that 800 are regular users of vitamins. Test the suspicion that less than 25% of people use vitamins. So we begin. This is a test. It's known as a test of hypotheses. Hypothesis test. And let me do it like this. So what we do is we begin with a statement. This is called the null hypothesis. Oops, something happened. Okay. Null hypothesis. This is what we hypothesize to be the case. This is what we hypothesize to be the case if there's nothing new. So the status quo belief that everyone has long had is reinforced by your experiment, or your study, or whatever it is that you've done to collect a sample. Okay, null hypothesis means nothing, null for nothing or no effect. Okay, so that would go here. And we have to first put the parameter in. Now this is a study of proportion, so I'm going to use P, and whatever I put there, I also put here. This is called the alternative hypothesis. If we find evidence to suggest things are different than the status quo, then the best guess or our conclusion would be to support the alternative. So these have to be mutually exclusive statements. I'll erase this. And so I put a P here and a P here. Remember, because these are the true values. We don't know them, and we're trying to infer what they would be. So I put an equal sign there. And then whatever number I make it equal to, I also make it equal here. The sign that I put here, like I said, should be mutually exclusive from this one. So I can put less than, greater than, or not equals here. Those are my options. So to avoid making mistake, I always put equals here, and then I figure out what is the status quo value to put here. When I read this problem, the only thing I see about status quo is this 25% figure. So 25%, let's say, is the status quo. And then we want to check that against less than 25% of people use vitamins. Okay, so I'm going to put this in a different color to remind you, you get to choose that. You choose. Not choose, but you use the best of those options. All right, so this is the null hypothesis versus the alternative. And what we're going to continue to do now are the 5 steps that I call the HAP-C steps. The first one is hypothesis. The next one is stating our assumption. Then we're going to assess the evidence. Then we're going to calculate what's called a p-value, and then we're going to conclude. So if you carry out these, practice with these 5 steps over the next couple of weeks, you're going to have no problem with this portion of the course, okay? So we have made it, so science, right, is about disproving hypothesis. So this is the null. This is what I propose to be true, and then I try and find evidence against it. So what evidence do we have? So let's go to the next, well, first we got to go to the assumption step, which is pretty much stated here, but I want to make it, I want to derive the results that follow from the assumption. So let's do the assumption step. So this was H. Now let's do assumption. Assume H naught is true so that P is actually equal to 0.25. So if P is equal to 0.25, we have some results. So we move from number 4 formulas up to number 2 formulas, and we know that then P hat is approximately normally distributed with a mean of 0.25 and a standard deviation of 0.25, 0.75 over 900 square root. Because this is our n here. And then what is this? This is our x. This is our count. So we assume the null is true, because if we don't assume that, we have nowhere to go with this. So we have to we have to make a statement and we have to refute it. We have to attempt to disprove it. So then going back to number 2, and I'll show you again. Actually, you know what I'll do? I'll drag it over. So it's going to be burned into your memory that this is the result. Gotta find a better way to deal with the number scroll. Okay. So I'm gonna put it here. In the corner so you can see it. So like I said, print out the formula sheet and keep it nearby so you don't have to scroll like I just had to. Okay, so this is the result I'm using. So for x that was binomial, there's a sample proportion, and it has a mean of p and a standard deviation of p hat. In our case, I'm going to write this. Let me write this a little more revealing of what I'm doing, that it matches. So p is equal to p0 is equal to 0.25. So this should be p0, and this should be p0, 1 minus p0 over n square root. So it's as though I have the value of what p is, and I put it in there, okay? So when I calculate this, I get a number, and that is my standard deviation. Now what? So we've done step 2. That's the result we assume, and then these results fall out. And now we're going to assess the evidence using that result. What's the evidence? What evidence do we have? We have a sample, and that provides us evidence. That p hat is equal to 180 divided by 900, or 20%. So let's sit back and look at this. I'll give you a moment to catch up, or let's see. So what happened is we made an assumption that the 25% of people use vitamins, and we're going to test if less than 25% use vitamins. By chance that we got that, we have to rule that out using statistics, because in fact it looks like less than 25% use vitamins, but we can't just conclude and say, well, that's true. We have to verify that that's a good, that's reasonable enough, reasonably low enough to say that this has some evidence to support it, that in fact less than 25% use vitamins. All right, so we're going to assess the evidence using statistics. It means that we're going to use the properties of the sample proportion. What are the properties? It's right here. That they should be, the sample proportion is among several sample proportions from all possible samples that are normally distributed with this mean and standard deviation. So what we're going to do is standardize this and see if it's a strange result, or if it is not strange. If it's strange, way outside what's acceptable for 25%, then we'll have to deal with that. We'll have to say we found evidence against the null hypothesis. All right, let's see. So what we do is we create Z. Z is p hat minus the mean of p hat divided by the standard deviation of p hat. If this notation bothers you, that's fine. Don't have to write it. Just write in the numbers. But I want to show you what I'm doing. So this is 0.2, and I want to standardize using I'm just going to write it like this. I'm going to just write it in words. So I'm going to minus the mean, which is assumed, and then I'm going to divide by the standard deviation, which I've rounded to that. So I round to 4 decimal places whenever I deal with p. Okay. So yes, there's lots of P's, right? So there's P is the true proportion. P hat is the sample proportion. And P0 is the hypothesized true proportion. It's the best guess. So these are P0. So yeah, you got to be clear. And I know it's confusing when you're just learning, but hang in there. So we don't know the true one. We are going to guess that it's this, and then we're going to use a sample to see how good our guess is. That's the approach here. Is that okay, Alec? So in reality, we don't know these parameters. All we've done for the last 3 months is I give you the parameters, you give me the probabilities, and we really need to use that theory that we built to do the more realistic thing where we don't know the parameters. All we have are samples. Okay, so let's standardize this and give me a number for this for this calculation. So it's confusing, right? We have 20 and 25. Are those, the question is, are those different? Are they statistically different? And statistically meaning what we're doing is we've created an approach where we talked about intervals. An interval is like a substitute for just one estimate when you know there's variability. So we're going to say, well, they can be a little bit different because there is variability, but if it's too different, that's the question. Is it so different? So how many standard deviations away from each other are these numbers? So we reduce it to something we understand, standard deviations. So somebody tell me, what does this mean? Or what does this imply? So what does this mean? So we found out that our result is 3.47 standard deviations below the mean. Is that unusual? What do we refer to observations more than 3 standard deviations? How do we refer to observations more than 3 standard deviations from the mean? That's right. It's outliers. So outliers means that we found something unusual. So what's wrong? Let's go back. So what we did was we made a statement. Because we had nothing to do here. We have no way to proceed without a population parameter, so we'll just make a statement about it. We'll say it's 25%, and then we're going to grab some evidence to verify against this statement. Now, if the statement fails, then we believe from prior anecdotal evidence, just people, things that certain people have reported or seen without a proper experiment or sample collected. So it appears that it's less than 25% of people. So we begin with a statement and then we test it. If it is 25%, then this should be the distribution. When we get a sample, let's test the sample, assuming the sample was a good sample, right? There's nothing wrong with the sample. Then finding an outlier, in our sample we found the sample is an outlier result. Sample provides an outlier result. So something's wrong, and it's not the sample. We actually found evidence against the null hypothesis. So we're going to drop our assumption. So something's wrong with the assumption. So really, after 3 steps here, we're really done. We see that we found an outlier, and we should be done, but we want to be more rigorous, and we want to report the answer in terms of probabilities as opposed to in terms of a Z-score. So that makes it possible for more, somebody reading it being able to scrutinize the result much easier. Okay, so let's see. We're going to calculate what's called a p-value. P-value is a probability. It is the probability. It's another way of reporting the 3.47. The probability of seeing a Z-score as extreme or more extreme given H naught is true. That's the best I can do for a general statement. So p-value is the probability of seeing a Z-score as extreme or more extreme given H naught is true. What am I talking about extreme? So far I haven't done anything with this. This is where I'm going to check. Extreme. What am I meaning? Extreme. I want the probability that Z less than the Z-score or I'm going to call it, I'm going to give it its official name. It's called the Z statistic because that's what it is. It's a statistic. This is like Z stat, right? So I want to find the probability of the standard normal distribution or the standard normal variable being less than the Z stat I calculated. So this is a statistic now because it's the results of a sample to calculate it. And I check to see what's the chance of it being. So what I'm checking is, since this is over here, negative 3.47, what I'm calculating is this. Okay? So rather than looking at it being an outlier, I want to know the probability given that H naught is true. So I'm still using these results here. This is the standardized version of that. So let's find the probability. Do we have that probability in our table? It's here. So it's 0.003. So the chance of seeing that result Okay, so Alec is asking if we got a 0, if we got Z score as 0, yeah, we still have to calculate this. I know, like, we have the answer, right? So if it's in between, so his question is, if it wasn't so far away, okay, let's finish this and then I'll answer Alec's question. So the answer is 0.0003. So this is so it says the chance of seeing the result that we got is so small. It's 0.003. It's a very small chance. It's like 0.03% chance. So what do we care? Is that a small chance? Is that a big chance? So basically, what I'm telling you is we're going beyond saying 3 standard deviations is an outlier. We want to be very precise about what we're saying, and we have to build a standard for saying something is unusual now. A different standard, not just 3 standard deviations is not going to be enough, okay? We want to be more rigorous. So what we're going to do is say the chance of being out there, if this assumption is true, is 0.03%. That's how strange it is. So a threshold is set for strange in most studies. And in this class, I will use 5% to say that any p-value less than 5% means you should reject the null hypothesis. Something's wrong with it. In general, though, we usually test to see if it's less than alpha. We call that the level of significance, but usually we use 5%. So this statement is true for all hypothesis testing. Okay, so this is the general statement. And so now I get to Alec's question, what if it's not? In this case, it is less than 5%. It's 0.03%. Let's assess that, and then I'll tell you the flip side of this statement, because it looks like you might lose your attention. So let's test it. So p-value 0.03, no, 0.003 is less than 0.05, so reject H naught. And what does it mean? It means a few things. We say the test is significant. We can also say there is evidence that less than 25% of people use vitamins. Questions? The number was, I got it from here. Like the drawing, I used the Z table and I looked up this number. So it's using, so basically in this step, what you do for this step is you take the sign from the alternative hypothesis and you put it here and you assess this statement. So there's a couple of things to say about that. If the sign goes the other way, you have to assess on the other side. If the sign has not equals to, you have to assess on both sides. We're going to talk about that. We'll do some examples. But for now, that's what we do. Okay, absorb this, and then I'm going to explain what happens if we don't reject. So for Alex's question about what if we got a 0 z-score, what do we do? Or z-stat. I keep on calling it z-score, but we'll call it a z-stat. Okay, so now, if p-value is not less than alpha, then we say we fail to reject. We fail to reject, and we can say test is not significant. And we say we have not found sufficient evidence against the null hypothesis. Notice we do not say we accept the alternative in this case, and we don't say we accept the null in this case. We just talk about having a lack of evidence. Okay, because we have to remain always open to more research. Science is never settled. Don't let anybody tell you any different. So if we got a 0, then what would be the z-stat, Alec? If we got 0, the z-stat would be 50%, wouldn't it? Because it would be here. The z-stat would be here. And the probability of being less than it would be 50%, and we would fail to reject. So we would fall in this camp. So as I said, we already had the answer being 3 standard deviations away, but this gives us a probability that we can compare against a threshold. I mean, we could have done that above as well, but this standardizes the way that studies are done, okay? So that when you read a study, you can just jump to the results and look at p-values and tables. This is essentially what it's for. So people can look at p-values, and even sometimes giving the threshold is, they give it, and people will say, oh, this is less than 0.05, but they might also mention in a table kind of format with results, they'll say 0.0001, you know, they could use that as the alpha. And sometimes people will go high and they'll let an alpha be less than 10%. They'll let things be strange as long as it's 10. So what's the difference between using different alphas? Well, you can see if you want to make it harder to reject, so you're more conservative, you use a very small alpha. If you want to make it easier to reject and say you have something new, different from the status quo belief, you use a higher alpha. So that's where we're going with this. This is science develops knowledge through rejecting these hypotheses, disproving hypotheses. So you need to make a statement, and then you have to get evidence, and then you have to try and refute your hypothesis. If there's some debate about whether you should be refuting things or not, reporting a p-value allows the audience, anyone reading it, to decide if it's good or not. Then they just have to compare these numbers. Like they'll just say, oh, in this case it's pretty small, but it's not smaller than 0.0001, so you can make an argument, someone can counter your results. Right, the very precise one. Well, yes, in science experiments you're going to try, you want to be careful, right? You want to be careful about admitting new drugs, for instance, and saying they're effective. You want to be more rigorous. If you're just trying to publish stuff, you might go with this one just so you're easier to reject. So what does rejecting mean? Rejecting is the substance of a publishable manuscript. Okay, so rejecting is very, people want to be rejected. They want a significant test. So as much as it sounds weird, you have to remember in your mind that science is about disproving hypotheses. It's going to give you a significant test if you reject H0, and you have something to report, something new that people haven't seen before, and something significant to say. So that's it. I mean, that's how you deal with hypothesis testing. We've done all 5 steps, and we did this for the case of a left-sided test, but it's pretty much, except for this step, the p-value step, it's the same sort of process. Okay, let's Should I continue? So it looks like a lot of work, right? 5 steps, but it lays everything out, and you should practice with these steps. And what we've done right now is for the proportion. This is for the sample proportion. Okay, can I continue? Take a screenshot? The answers are all here in the notes anyway, so I've put all the answers there. And then I have some graphs here. So okay, so here's the graph for what we just did. So we did this. We found the z-stat. I have a different result here, but it's okay. So negative 3.46, and then we found this here. My numbers were pretty much the same. So we got the p-value and we got the z-stat. That's what we did. But it's interesting to ask at what threshold, which z would have made me reject. Did I need to be that far out? Well, no. All you had to be at was about here, right? Because this creates 5%, and that's what we compared it against. So you didn't have to be so much an outlier. You only had to be 1.646 standard deviations below. And that creates the reject region, and otherwise your fail to reject region. So for a one-sided test, it's 95% of the observations here and 5% of the observations here. Now, after the step of calculating the z-score, we could have just ended things and said, oh, it's less than 1.646, that means it's an outlier, and we have to reject the null hypothesis, and we could be done with it. That's in fact how I learned things 25 years ago when I learned this stuff. Well, 25 years ago? Is it 30 years ago? It's probably 30 years ago. Anyway, so but what we do since then is we actually go through those extra 2 steps to make it much more standardized conclusion, calculating the p-value and presenting the p-value as opposed to the z-stat. Okay, so let's try another one. I have lots of problems on vaccines in here, so that's kind of interesting in this day and age to be dealing with. So let's see. Okay, Gerardo's asking about the different kinds of tests. So we're going to do that. So what you do if you have, let's do it here. So let's say you did a left side test. Then this would be flipped the other way. And we would be checking on this side. But for a two-sided test, we have to do something completely. We would have to, for the two-sided test, we would test against the p-value being with 2%, 2.5% here and 2.5% here. That would create the fail to reject would be defined here. We'll deal with this in a second. Okay, so it's a little bit different. What you actually have to do is calculate your p-value on one side and double it, because you need to check if it's higher or lower, if it's not equal. So this is the case for HAP not equals to 25%. Well, all right, 0.25. So you would have to It'll make more sense when we do it. So just be ready for it. It's going to be different. And because it could be on the left or the right, so when it's not equals, it can be higher or lower. So that'll give if it's higher, it'll be a positive z-stat. If it's lower, it'll be a negative z-stat. So you need to take the absolute values and calculate just to be less than, but multiply by 2 anyway. You have to compare on both sides, so it means duplicating the p-value. Anyway, we'll deal with that in time to come. Okay. All right, guys, let's go to the next problem. So maybe I can give you some time to try and lay it out. And yeah, I'll leave this on the screen. So let me give you 5 minutes to try and read that, and then we'll meet back here, okay? 5 minutes. Okay, I'm back. So how'd you do? So one measure that is of critical importance for practice of modern medicine is the proportion of patients that experience an adverse reaction to a vaccination. Some clinics examine every record to determine that proportion. In a large practice, though, taking a census of the records can be time-consuming. Suppose a random sample of 2,500 patients is obtained from a large clinic. Also assume that as a result of past census studies, it is known that the proportion of patients who have an adverse reaction is 1%. So what is the approximate shape of the sampling distribution of the sample proportion? So again, from number 2, so right now we were told that there is some sort of p known, right? So p is known to be 0.01 for adverse reactions, where the variable is adverse reaction. This is the true proportion reaction. So what do we know about the sampling distribution of the sample proportion? Remember, sample proportion is p hat. So p hat then is approximately normal with a mean of p and a standard deviation of p1 minus p over n square root. So we got to figure out 0.01, 0.99 divided by n 2500 square root. So this is the result for the sample proportion from a sample of 2,500. Oh, I should leave room to calculate it. So then you put the number in there. So it's 0.0020. Oh, this answers A and B in here. Because I did the mean standard deviation and the shape. So the approximate shape is normal, and that's the mean and standard deviation. Now, what is the probability that more than 2% of the patients in the sample will experience adverse reactions? So given this information on the, let me write it a little more cleaner here. So p hat is approximately normal, 0.01, 0.002. What is the probability that more than 2% of patients in the sample will experience an adverse reaction? Is what we want to check. So we want to see that the sample result will show more than 2% of patients have adverse reaction. So we can use the results above to standardize and find the answer. So what I'm doing so far, this is not inference, right? This is just the results of the sampling distribution of the statistic results. So far this is all results from So what's the chance that more than 2% of patients will experience adverse reactions? We say that it's, this is off the chart, it's just 0. There's no chance. Questions so far? And now I want to do the hypothesis test. Ready? Just to be clear, that's going to be 0. Ready for the testing of hypothesis? I think this is a 2-sided test, so we get to try that now. So proponents of vaccines believe that the likelihood of an adverse reaction is very small. They actually believe it to be 0.1%. They also insist that they have evidence to support their belief. If from the large clinic, 100 people out of 2,500 were found to have an adverse reaction, is this evidence against the claim of the public health? So let me see. I have all the results here. So what we're going to do is use this new information, and this is for proponents of vaccines. And we're going to try and disprove this statement. Okay, so we'll say they believe they have lots of evidence, and then we're going to take a sample to test their evidence. So we're going to say they believe this to be true, and we're going to look to see if it's not true. And so this is the first step. Remember, this is the hypothesis, the statement. That's what the status quo belief is. And the alternative is what we believe to be true if there's evidence against the null. So we have to test disproving the hypothesis with evidence, a sample. So first we have to assume H0 is true. So that means that the true proportion is equal to the hypothesized proportion, or 0.01. Remember, this is just P0 here. And how I did this was remembering I use whatever number I put there, I also have to put below. And I'm going to put this in a different color to remind you that we get to pick which test we're going to do depending on the question. But otherwise, everything else in black is, every question on hypothesis testing is always like that. Always do it like that. So we assume H not to be true, so we assume that is 0.001, and as a result, that means that in a sample the sample proportion will be expected to be the true proportion, or this hypothesized one. And that will be with the standard deviation of this. So we have to calculate that. And what do you get? Let me just make sure I'm getting it all right. Did I make a mistake? Let me do it again. Oh, right, okay. I'm doing it with the HAPC method. That's why it looks different. Yeah. So, okay. But where is that answer? I guess I didn't do that. Okay, so I didn't do this answer. So let's just continue. This one is not in the notes. All right, so now everyone has my answers? I'm going to take this to another page because I'm running out of space. So the benefits of teaching this way. And then we assess the evidence. Our evidence was enough to give us a sample proportion. It was 100 people out of 2,500. So 100 people out of 2,500 had an adverse reaction. So what is that? It's really high, right? It looks very different than 0.001, doesn't it? It's very different, but we need to turn this, we need to convert this result to a standardized value. So we want the Z statistic. And we're going to take our p hat and we're going to minus its mean and divide by the standard deviation. And we have 0.04 minus 0.001 divided by 0.0006. Let's see, what is that? With such a small standard deviation, that should be quite big. What do you get? I already have a sense that we're going to reject the null, but let's continue with all the steps. It's a huge number, right? 65 standard deviations. 65. So now we're going to do the p part. So the p-value is equal to the probability that assuming that the null hypothesis is true, the probability of seeing a z-stat as extreme or more extreme. So what we're doing is we're going to mark 65 and we're going to mark negative 65. Now we're just adding zeros here. But this is the process for a two-sided test. So we really have to write that the p-value, so you can just draw this, you know, you don't have to, you just draw it. For this step, you just draw and you translate from, this is because there was a not equal sign. The p-value uses the alternative hypothesis. So I have to check on both sides, and the p-value is 2 times the probability of being less than that. So if it was a number, I'd have to put it there, but we're just going to multiply 0, and it's really just 0. Probably why I didn't put it in the notes. I'm not sure why it's not there. Most of my answers are in the notes. So when you read the probability of seeing a z-stat as extreme or more extreme, that's what creates this as extreme or more extreme. I want the tail probabilities. I want the measure of how unusual that it would be in probability, and its chance is 0. So our final step is the concluding step. The conclusion is, and you always write this no matter what kind of test it is, the p-value, which is 0, less than equal to 0.5. Because that's true, we reject h0. So this test is significant. And there is evidence to suggest that well, in this case, it's more, right? 65. But I shouldn't say that just because we didn't test it, but really it looks like more. But I would say just in the standard of the test, there's evidence to suggest that there are not 0.01% adverse reactions. There is the test is significant. The evidence, there is evidence. But I want to say it in terms of the, because we said not equals, but from the evidence, it looks like there's more. You need to write it in terms of the test first. So the test is significant. There is evidence to suggest there are not 0.01%, but more. And you can't say 4%. You can't use this result. It's just one sample, right? But there's enough evidence to suggest it's not 0.001. 001. Any questions? So when a test is two-sided, this is what you have to do. You have to get your result for the left side and multiply it by 2. I actually should make this a negative, shouldn't I? That's wrong what I'm doing here, because this should be, because the left side is negative, I have to make this, oops. Let me make this bigger. What I'm actually supposed to do here, and as it is in the notes, it's z less than, and then a negative here, because the left side is negative. Below, right? The negative represents below the mean. And then the same thing over here, where I did that. Oh, I wrote up here somewhere. Where did I write that? Over here. Here in the notes, there should be a negative in front when you go left. I'm being very loose about this because I don't expect you to write this. I just want you to understand what it means. I want you to draw this picture though and tell me what you're doing. And the picture, well, not this picture. I want you to draw the picture with a z-stat on it. So what you're going to do is, just like I did, you're going to draw this. You're going to put the z-stat here. So let's just do this with numbers. Let's say your z-stat is, then you put 1.2 here as a negative, and you put 1.2 here as a positive, and you would see this. And this would, you want to know the extreme values, you want to know the tail values for that z-stat. That is your p-value. That's why you have to multiply by 2. In the previous exercise, we had a different, I'm not sure what you mean. Which test? Sorry, Alec. Working on this, I thought we would get a different test result from the previous exercise. Which previous one? The next thing I want to do is this. Now we went through all these steps over here, but when there's a two-sided test, there's a faster way to solve this, okay? When there's a two-sided test, you have to remember that it's only for a two-sided test. Right, intuition is not always right, exactly. So for a two-sided test, a faster way, and this is only for a two-sided test, I can't stress that enough. A faster way to do this is just build a confidence interval, and in particular, since we use alpha of 5%, we're going to build a confidence interval of 95%. So alpha is like the tail probability that we permit, and outside of the 5%, we say things are strange in the tails, and then 95% is the confidence interval in between. So we build a confidence interval around our statistic. And then we consider So you consider all the values in the confidence interval as close to or as the same as the p-hat that you got. And then you check if your hypothesized value is in there. So let's just do that. Let's make a confidence interval. And you should just memorize by now that the confidence interval for 95% is 1.96, because we're going to use that a lot. So you're going to see that again and again. So we're going to make 0.04 plus or minus 1.96, and we got to calculate this here, which we did, right? No, we didn't do that. So this is 0.04 times 0.96 divided by 2500. And then so this is 0.0039, and let's make it interval. So let's go all the way and make this interval. Let me know if I make a mistake. I'm just going to keep 4 decimal places. So that is the 95% confidence interval created for the sample. And then we say, since P0 equals 0.001 is not included, that means our result is different from the hypothesized value. We reject. Much easier than the 5 steps for sure, but don't lose sight of what you're doing, okay? It's not going to be clear. So you've built a confidence interval around your sample result. Which you have an intuition to do, right? Just make a confidence interval. So what does it mean? It means that since the hypothesized value is far off from here, we have to reject the null hypothesis because values near to the p hat do not include it. So that's only for two-sided test. Can you do that? All right, so what I've done so far all day today was to look at the inference for P. It means you don't know P, but you're trying to guess at it. And we learned the 3 formulas that you need, and I taught you about left-sided tests and two-sided tests. And I think that's it for the test next week. I'm going to focus on these topics, but I'm going to spend the class discussing number 5 for means, okay? So for the test, it's up to here. Well, not up to this page, but it's going to be all of this stuff you should study for the test next week until here. So then what we're going to do is next week I'm going to talk about, this is for test 3. For next week I'm going to talk about inference on the mean, and then inference on the mean when sigma is known and not known. And then we have those 2 classes, like next week and the following week, just to focus on that. And that's good. I think that's good. If you guys work hard to understand this, it'll be very easy to do this for the mean afterwards. So what you should be studying are these problems in here. And remember, for your test, you're going to have to do, it's bin, SDS, and so this is unit 5. And then in unit 6, it's going to be on just inference on P. So in terms of the formula sheet, this is going to be 1 through 4. All right. So having said that, what would you like to do next? You want to do some more hypothesis testing? What would you like to do? If you don't want to do anything particular, I'm going to go to the new material, even though I'm not going to test it. Okay, so another one for P. In hypothesis testing. So let's go. The homework exercises in inference are more focused on the last material, so that will be confusing. So just focus. So just note that the homework exercises is mostly on the inference on X bar, so that will be what you can study for after next week. So let's see, let's do another proportions problem. I'm wondering if I should send you some more exercises because there's not a lot. Let me see the test that I have up. Let me see in the in Moodle. Doesn't memorize my credentials. Oops. Goodness. So here are, okay, you have practice questions. So let me see the inference. Let's see here. So notice, if you look at the inference problems, it talks about average time. That's not proportion, right? So that most of this is like mean and standard deviation. This is for the mean, mostly. Okay, so let's see the practice assignments. Again, averages, when it says averages, that's not it. Average. These are also for mean and standard. So these are all good for the final exam, right? You got to study all these for the final exam. Okay, that's what I'm going to focus on next week. And then this one. And you have those, and then you have the tests. I think you'll find more problems in the test. I feel like I should send you some problems. See if I can find another one here. Among these ones, there's some, for sure. Okay, so to estimate the proportion of people who favor to get rid of the goods and services tax, that's what that is. It's in Canada. To within 3 percentage points. Okay, no. If you randomly select, I'm looking for one. Okay, let's do number C. Let's do C. In a pre-election survey on the issue of the GST, an opinion poll company claims that the majority of people favor such an action. Okay, let's do this one. This is a good one. I guess I have to take the whole question. Hold on. Oh, Gerardo wants a question. Okay, let me do Gerardo's. I forgot about him. Because this will take longer. Let's do Gerardo's question, and then I can go back to this if there's time. Because you have the answers to this. Okay, a large city has 2,250,000, 64%. I don't think this is relevant, but I'm going to write it. So it's a large population, 64% support political candidate A. So P, that true proportion, is 64%. A random sample of 10 is chosen without replacement. So N is equal to 10. What is the P? What is the probability, I guess, that all 10 in the sample support candidate A? So the probability that all 10 support is the same as the probability that P hat is equal to 100%, right? So get your head around this, that's what you want to test. I mean, that's what you want to calculate. So let me clarify. X is the number it's the number of people out of 10 who support. That's the success, right? And P hat is the proportion of people in support out of 10. So you want to find the probability that P hat is equal to 1 or X is equal to 10. And we can check, can we use the approximation to do this? I mean, you can do it either way, I guess. We have all the information. So to use the approximation, because n times p is greater than or equal to 10, or n times 1 minus p is greater than or equal to 10, right? Because n, or is it? It's not, so you can't do it that way. It's going to only be 6.4, and this one won't be either. So you can't do the normal approximation. So you can't do the normal approximation. So the way that you're going to do this is the binomial. This is just a binomial problem. So when it doesn't work, use the binomial. With n equals 10 and p equals 0.64, what you want to find is you want to find so it's just going to be 10 choose 10, right? 0.64. So when questions get mixed up, you got to know how to tackle them. You cannot use normal approximation. So you have to use the binomial. So this will be to 10, and this will be 3, 6. And that will be to 0. So that should be the answer. Is it correct? Is that in the questions that are in the in Moodle? Sorry that I don't remember because I did that such a long time ago. Don't recall. I mean, I put them there long ago. Let me know, is that the correct answer? Yeah, like that should be Unit 5. Okay. So basically you have to use the binomial for that. So you got to know which one. Yes, you have to know which method, but if you do it correctly, you should get the same answer doing different methods anyways. Okay, so what I will do is I'll send you more problems for this, a couple, just not too many, just a few more for proportion. You know, I'm not going to send them. I'm going to put them in Moodle. I'm going to build that Moodle site. I should be clear what I'm saying here. For inference on P in Moodle. Okay, so I'll do that. I'll put them under Unit 6, sorry. Okay, so I guess I'll let you go. Not time to start anything. If you have questions, please contact me. Let me know if you need to meet or if you need me to make video or explain to you something. Please contact me. Don't let time fly. So the next test, like I said, will be bin SDS and just inference on a proportion. And then the final, it's supposed to be everything, but remember it's 40% on inference. So what we learned in the last 2 classes will be a good portion of the test. So be alert, be there. See you next week. Keep in touch, okay? Bye for now.